Hey guys, how's it going? So today we're going to be covering the meta segment anything model. So this model is quite fascinating actually. I think the computer vision folks felt like it was more like a ChatGPT moment because the model is so powerful to the point whereby it essentially allows you to extract a specific thing within an image. So I feel like how they've done things in a very smart way. One of the highlights for me was how they have integrated what they call data engine to continue to generate labels to the point whereby the model was generating labels automatically. So because of it's hard to kind of like get a label data for segmentations and how they thought about that, that was one of the key thing that they did. So I'll try to also show you how they have integrated these image encoders, mask decoders, prompt encoders in a more smart way and in order to get a very powerful model, right? So how we're gonna go about this is that I'm gonna be linking everything that I say to the paper, and I'm gonna be following pretty much the architecture that you're seeing currently on the screen. So the architecture will actually essentially lead us to which file we should start with, right? I think that makes sense so that we do things in a much more like sequential way, right? But the architecture is quite simple to understand. So essentially, we have an image and we have an image encoder. This is more like a VAT model. So this VAT model is going to produce image embedding. These image embeddings, they are going to be channeled by height by width, and this is going to be 256 by 64 by 64. Then we have this prompt encoder, which is going to take these inputs. These are prompts. It could be text, box, points, and mask. But the text, I don't think they said that they used clip for the text, but I did not see that in the source code. So I think they also mentioned that actually they did not include it. But yeah, the only thing that also in the source code is the box, is the points, and the mask. So we have that prompt encoder. Then for the mask, we use a convolution block. Then we have this mask decoder. You can think of this mask decoder essentially is going to map the image embedding and the prompt embedding and output token to a mask. That's why we're gonna get a valid mask there. So we're gonna start, as you can see from the architecture, we're gonna start with the image encoder. Then what I'll do is that I'll always come back to the paper, and everything that I say, I'm gonna make sure that I link it to this. For instance, I think if we scroll down, there's detailed page right here. Yeah, this is it here. So we're gonna link this part that we sync here to what we saying. So yeah, without wasting any time, let's get into it and see how everything works essentially. So this image encoder essentially takes the image size of 1024. They did say in the paper that essentially they're using the pre-trained vision transformer to process high resolution input. Specifically, they use the VIT-H16. So this is going to be our page size. So how VIT works, which we're going to get into in a much detail, we kind of like create patches from these image. So you can think of like we have an image and we try to extract these little blocks here that have a same size. The image is going to be that we take is going to have gray channel with its RGB. Then after we apply the page embedding, we're gonna be projecting these to 768. Then the depth of the block, this is a very heavy model, so it's gonna be 12. By block, I'm referring to that each block, after we apply the attentions and all of that, we're gonna do that like for 12 times. That's what this for loop does here. Then we have the number of heads. So this is more we when we get into the attention and how we have this multi-head attention. So we're gonna have 12. Then we have these multi-layer perceptron ratio, and this is gonna be the output channel. So what happens is that essentially we have to output after we done with this, we have to output a 64 channel by 64 by 64. That's what the model should output. That output will then go into into the next encoder. But that's the first point. Then we have these embeddings, which I'm going to explain, but I just want to give you a high level overview of all the inputs, but these things will be explained in a much more detail. Um, what we have here, we have this patch embedding. So this patch embedding's goal is essentially to extract these patch from an image. So how they do this is that they're using a convolution and they pass it a kernel of patch size. Just to remind you, a patch here it's 16. So that means we're passing 16 by 16 kernel size. Then we have stride, which determine how we should move within that. Then it's going to be 16 by 16 because it makes sense. We want to extract 16 by 16 pairs. So we want to go through all of that image, extracting those. We have in channel, and it's going to be in channel, which is tray. Then we have the embedding size. This is what we want the patch embedding to output. So after this, we're supposed to get these supposed to be projected to the 768. So how this work is that just gonna go straight to the patch embedding function so that you understand how it works. um, yeah, it's the one that is on below. So you can tell we're taking the same output that the input that I just explained to you. So we have this convolutional block. So I just want to explain this from a white document so that you understand. So there's different ways, right? How you can extract blocks from an image. There's multiple ways that you can go about this. For instance, you can have a for loop, double for loop, right, for each image here, and you have another for loop to take the patch, right, and you take another patch. Then what you're gonna do is that within this row and within this column, you're just gonna extract this patch, and you just continue doing that, right? Like, and you load this inside some sort of like a box. Then you have these patches. That's one way you can go about it. But in this case, the reason they're using convolution also for efficiency is that essentially convolution, how it works is that it's going to have this kernel. I'm not sure if you know the convolution, but I'm going to assume you don't. So we have this kernel. So we are told that, okay, this kernel is going to be 16 by 16. And we know that our patch size here is going to be 16. So given this image, which is, we are told that it's going to be 1024, it's going to be 1024. So we want to go through the image and extract that. And we know that convolution can help us do that. So what we do is that we say that the stride is going to be 16 by 16. So this is how we move within this image. So if we're going to move this way, 16 by 16, which means that we're going to come here, right? We take the first 16, we go to the next 16, we go to the next 16, we go to the next 16, just like so. So hence it is important to make sure that your special dimension are divisible by this patch size. In this case, if you divide 1024 you by 16, you're supposed to get 64. That's what you get here, right? If I'm not mistaken. So then that's what we're gonna do. It's gonna go through all of this and we're gonna get the output. So your question now might be, what will the output be after we apply convolution? So we can use the convolution equation to understand this. Let me just change my color. So we can take the special dimensions, which is going to be 10 by 24. Then we can actually add the padding. In this case, I think they applied zero padding. Then we can actually subtract the kernel, which is going to be 16, and we can divide by the stride, which is going to be 16. Then we can add 1 here. So I think there's 24 plus 0 minus 16. We're gonna get 008. Then we divide by 16. We get 63. Then plus 1. We're gonna get 64. So what does this mean? It means that essentially after applying this layer, um, the activations of this convolution will give us that it's going to be batched by the the output channel, the output channel, which is going to be the filters. I think in this case was 768. I'm not sure. Yes, I think it was that. Then it's going to be this, which is 768. Then it's going to have this height and width of 64 by 64 that we attain from here. So this is what we're supposed to get right after this layer. But the point here, just to kind of like remind you at the high level, that the point is still the same. We just want these uh, these patches here. So you can think of what this 64 means is that within this height, there's 64 patches. So we're gonna go within this and extract these. And within this width, also there's 64 patches that we want here. So hence it is important. Hence you'll see most in source in other source code, you will see that it's important to make sure that your dimension, your height is divisible by this patch size, because it has to be, otherwise you're gonna overflow, right? So it has to be divisible. But yeah, I think that's like the intuition behind this. But anyway, let's go back to the source code. I just wanna show you how it's kind of like being done from here. So this is what they did, which is they had this conv2d and they pass in the in channel, in this case was 3. Then the embedding dimension is 768. Then they have this kernel size, stride and padding, which is 0. Then they get this badge channel height by width, and they permit this to be batch height, width, and channel. I think it's very important for us all the time to keep track of these output dimension, because of this way we get to understand in much deeper way. So I'll make sure that as much as I explain after each function or operation, I ask myself what the dimension will be, because this way we get to understand how the data and under which dimension is getting processed. So anyway, let's just continue and try to understand also what will happen after we have applied this patch embedding layer, is that we will get that output that we had, and we have this absolute position. So if like use absolute position is true, then we gonna create this absolute positional embedding. So some of you might actually ask yourself, what is the absolute positional embedding? So there's this there's different type of positional embedding. So there's like the technique whereby we use the cosine and sine. There's a rotary embeddings, and this time they're using this absolute positional embedding. But you can think of positional embedding. It encodes the position from 1 to maximum sequence length. That is, each position has a learnable embedding vector, right? So the positions in this case are learned jointly with the model. That's why we have this NN parameter here. So they're going to be learned. So that's what this positional embedding will do essentially. So just to kind of like explain what's going on in here. So you can tell here, like it takes the image and divide it by the page size. So it takes this and it divided by the patch size, and it does the same thing, and it passes the embedding dimension, and which is true, because if you look at the transformation that we get here, it's literally the same thing. Let me just scroll down just to make sure the dimensions are correct. So we have the badge and they have height, width, and we have this is 64, by the way, because we saw in how we did it on the whiteboard. So this is 64, and that by that's 768. So we have a badge. In this case, we can see that actually it matches what we see here, the embedding size and patch. I think it is because of we need to add this after to those patches. We need to add that that the position in this case, right? So that's let me just validate that or verify that. So we have this patch and we add that to this self.pos embedding, so which is this. So this is true. That means that that's why the dimensions are like this. So the dimension matches with what we get here. So it's just important. So I'm just saying this, maybe some of you might deem this as unnecessary, but I feel like understanding these dimensions does help. At least for me, I feel like it helped me especially to understand PyTorch in much more intuitive and good way. So I'll try by all means to kind of like go into more detail in these dimensions within these blocks. Nevertheless, we have this block here. So I want to go through this block, but what I'd like to do first is to cover the things that are dependent on this first, because that makes sense. For example, this is the block, but this block is dependent on this attention. So you see, I think that way we better start with attention and look into the multi-layer block or something like that. Then yeah, we let's look into this attention layer now. So the attention takes the dimension. This is still the same dimension as like that we were working on with the positional embedding, which is the 768. Just to show you that, as we can see, we pass it here and it's coming from the block, and there is it here. So it's the embedding dimension, and which is we define it here. So it's still the 768 in this case. Then we have the number of heads, which is 12 by, but by default here they put 8. Then we have the bias of the query key and value. We're gonna be using the relative position, which I'll be explaining what it is. Yeah, and that's that. As usual, we gonna divide the dimensions by the number of heads. So this is give us the head, because that's what we gonna project the dimension into these number of heads. I'll explain the attention also in a little bit. Then we have this self.query key value, in which we're trying to project it to this. I think it's going to be, what is it, 768 by 3, 23008. Um, then what does that signify? It just represent the query key and value. So what you will see most of the time is that some of the authors replicate this 3 times, and they just have dimension just like so. But in this case, I think they did it this way. So I think it's still the same thing. This is just another linear layer that we're gonna use. Then we have this user relative position. So what do we do with this relative position, which is gonna be, it's gonna encode the positions of the patches across within the attention mechanism. As we can see that we take this, the first number of patches across the, I think this is the height dimension. Then we take also the number of patches across the width dimension. Then we have a height dimension here. So just to kind of like give you context around like relative position. So with like positions, right? Embedding, how we do it is that you can think of it as like we give each token or each patch some sort of like a position. Like it could be like how we define it with how we define the first. That's how we could go about it. But what happened was that I think in 2018 the authors from Google, they introduced this relative positional embedding, in which like this is more flexible by that it can dynamically adapt to like different sequence lenses. And how it works is that you can think of like each token in the input sequence, right? It's gonna have positions for each other tokens in the input sequence. For example, let's say we have one, I don't know, like this is like, just think of these as tokens, like, or patches, so to speak. So this first patch here is going to have position of itself. It's going to have position of the second. It's going to have position to encode the second token. It's going to have position to encode the third token, just like that. Even this one here, it's going to be -1, which is going to be going back. Then it's going to be so we're going to have a second number here, which is going to be 2 to encode itself, just like that. So you can think of like we have these within like each thing. We have these things that represent the positions. So the intuition behind this, it is like it can work within, if like you have a graph data, it can still work fine, because now, like, with graphs there is no like some sort of like a sequence in the graph, like, right? So like I can be related to someone, that person can relate to something, they can be a cycle or something like that, right? So now the now, like the reason they're using this within the attention mechanism is because we can't sum those things. Like if we're about to sum it, then it will be pointless. We're making that pointless. But we're using the attention because we want those tokens that within each patch, we want those, so let's say positions within that each patch that relate to other token, that the other patches, we want them to relate to other patches. So we know that the best thing that does that is the attention. That's why we include this within the attention mechanism. So we include it so that when we do the attention, essentially we also, the attention is also relating each patch in terms of their position. So I don't know if you know the YouTube channel by Miss Coffee Bean. Yeah, check it out. I think she explained it much better. I'll leave the link. But that's like how it works. So that's like they're gonna apply this across the query and the key. We're gonna see how this is getting applied also from the code perspective, but that's how they're gonna apply. As you can see that they have this head dimension from here. Then we're gonna have this forward pass in which we have to apply this query key mechanism. So what's going on here is that we're gonna get this input. Though this input here, it's gonna be the input that we saw, if I'm not mistaken. So it's gonna be this input here, batch by what was it? It was height. It was width by C, right? Just to make sure that we correct. Yeah, that's fine. So um, yeah, that's fine, right? So what we see here is that I've been actually I wrote this prior, but anyway, what we see here is that this self dot uh, KQV is like it's gonna take this, right? It's gonna take an input, right, and it's gonna project this channel, which is 768, is going to project it to 2308. That's what it's going to do here. So we're going to be getting um, batch height by 23. So it's going to be 3 here. So this is going to be, let me just paste it here so that you can see. Just going to make sure that you can see. I'm going to paste it here. So that's what we're gonna get. Then we reshape this, right, to this. So what's going on here is that we, because of each patch, you can think of this as a sequence length. So we have like these patches, which is number of patches. So this is 64 by 64. This is supposed to give us four something, 40. I forgot four something, but yeah. Anyway, then we have this tray which is going to represent this query key value. Then we have this self number of heads, which is that. So how it works is that essentially the dimensions of this, like said, that's 768, it will be projected to these number of heads. Then that's how it works. Then we permute this to get 3 by b by number of heads and number of patches and channel. So let me just visualize it for you. Let's scroll down, and I think that way you can actually get to understanding much more intuitive way. I hope I'm good at visualizing. But anyway, we can think of like we have these patches, right? How many patches do we have? Like all the way, like I'm talking about the patches from the image. So we know that it's going to be 64 by 64. Where is this coming from? We said that we're going to take an image and we divide it by the patch size, which was 16. So we took 1024 and we divided by 16. We got 64. But because of now we have height and width, then we have to multiply this by 2. Then that's what we're gonna get. So now you can think of this as like we have the sequence length. I'm using the same term from the natural language processing, but this is like sequence length. We can think of this as a sequence anyway. But anyway, this is the sequence length. Then you're gonna multiply this by each page. How we said that we projected it to this 768, right? So it's gonna be 768. Hope that makes sense. Then what we do now is that we have these queries and key, right? Like so. In that case, you saw that they made them to be one thing, but I'm just gonna kind of like separate them, but it is still the same thing because each one of them is gonna take it's gonna be 768 by 768, 768 by 768. But in the paper what they did, so it's like they squeezed them into one. But anyway, we gonna be having this, right? And what the goal now is that we're gonna take each patch, and we're gonna, by the way, this is not three. I just wanna emphasize this. You're going all the way to for something here. So this is for, I forgot, 96, I'm not sure, but yeah, 496. Then you're going all the way to 496. Then this is only three of these. It's only three of these, right? Then what you do is that you're gonna project these um, into into you're gonna take this dimension and you're gonna have these heads. So in the paper they said that it's 12. So you can think of like this 768 is gonna be divided. 768 is gonna be divided by the number of heads, which is 12. So you have these number of heads here. Okay. So we have these number of heads here. And this is for each this is for each patch, by the way. Like I said, we still have 496. So it has to do that, right? So you still have that. So each patch here has to pretty much get each, it has to go through each query, key, and value. So that's how it works. So that's how I'm trying by all means to visualize this. I think this is going to be transposed, but then now we're going to have to get into the dot product attention to calculate the score essentially. But that's like how it kind of like looks like at the high level, I think. So just to kind of go back to the code, so that we can continue. Then you can see that we use this unbind now to extract the key query key, because the reason we have to extract them is because we have to do this dot product here. Like we have to essentially take the queue and multiply it by the keys, and we multiply it, and we have to scale this query by the scale, which is the head dimension squared minus 0.5, and that's what we do essentially. This is going to give us that tension, so between these. So yeah, um, actually before we continue here, I just want to say that this unbind essentially is going to extract the query key and value. So that's why we have this zeros dimension. So it's going to extract these dimensions. So it's going to take 0, 1, 2, right? That's what we're going to have here. So then we apply this attention. So what we do here is that we apply this transpose. So we're transposing the two last dimensions. So because of now, we have B by number of hits, then we have number of patches, then we have the channel. So what will happen is that we essentially going to be doing a matrix multiplication across the two last yeah, the last dimension of the query and the second last dimension of the key, which is the dimension, the C essentially. So maybe if I confused you here, so you can think of K as it's going to be B by n head, right? N head. Then it's gonna be the number of patches, which is W by W. Then it's gonna be, we transpose these, so it's gonna be C here because we transpose the last two, so it's gonna be C, I think. Um, right. So yeah, I think it's just three values here. So now because of this, what's gonna happen is that we take the C. This one is still gonna be the same, so it's still gonna be this. The the query. so to speak, is still gonna be this, right? So now what will happen is that when we do a dot product between these two, is that we're gonna do it across this dimension here. So this C here. So you can think of now the output will be what is it? B by head, right? I think it's gonna be what is it? B by n head. Then it's gonna be by n head. Then we're gonna be having the number of pixel, which is height by W, and another height by W, which makes sense intuitively because of you want each page to see each page against another page, like what's the relationship, like what's the score, like in terms of like you know I don't know how to explain this, but you can think of it as like you want to understand like if like this page is related to this and by which score, by amount of score, so something like that I think. So but that's what we're gonna get anyway. What we do inside here, we add the relative positions, which I told you, and we're gonna do this across the query and the key. And we have this self the relative position on the height and width. I think this is because of we extracted the height, the number of pages across the height and the width. That's what we're gonna do inside there. Then we apply the softmax to get the probabilities. Then what we do is that now we do an attention on the values. So how you can think about this in a more intuitive way is that you can think of the query as like it's going to ask what am I looking for. Then this is more like then the K is like what can I offer. Then the V is like what I offered. So we're trying to say attention dot this to the attention dot product v, like to get what the v can offer, or something like that. I'm trying to be as intuitive as possible because these concepts sometimes I feel like we overlook them, but I'm trying to make sense of them from a simple English in a way, like just so that we understand like why we're doing these transformations. But anyway, that's what we're gonna do, and we're gonna reshape this to be batch height width in the channel, and we're gonna pass this into the self projection, which was actually, just to remind you there, where is it, which is gonna take the dimension and it's gonna project it into dimension, so it makes sense. So which means that we're still gonna be getting batch height width and this dimension, so that's fine. Then we return x, so we still have pretty much 768, but we know based on the paper, when we read the paper, we know that the output should be 256. So that means this has to be another component within this code block that has to do that, and we're gonna get into that. But anyway, let's now go into backtrack because of there was something. Yes, this is it. So we do understand this is attention mechanism. So now we have to kind of like log into these other ones. So the attention layer, it's going to return that 768. Then we have this norm layer in which is gonna apply. We're gonna apply the normalization layer across the dimension, which is gonna be the 768, right? So I think this norm layer, it's been defined somewhere, but I think it's just the linear layer, and then layer norm. So that's pretty much it to this. Then we have this multi-layer perceptron block in which we're gonna pass in the dimension, and we're gonna get the dimension by multi-layer perceptron ratio. But before we do that, let's go to this file. So we can see that the multi-layer perceptron, it essentially it has these two linear layer, and it's gonna project the dimension to this embedding dimension. So it's gonna literally give us the same input. Yeah. So it's more like a bottleneck because you take this small dimension and you go to this large dimension, and then you go back to a small dimension, right? Because here, obviously, this ratio here, we have to multiply what is it in this case? You see here we multiply in this dimension by this multi-layer perceptron ratio, in which is 4. So if we do the math, we can see that we're gonna say 768 by 4, we're gonna get 3072. I hope my math is right. Yeah, I'm not, but I hope I'm doing the right thing. But yeah, because it's the dimension, right? Which is we passed it here. So this dimension is coming from here, which is the embedding layer. So it has to be 768. Yes. So that's fine. I think we're doing the right thing. So that's what we're gonna do. But yeah, I think this is just more like a, so it kind of like take a small like dimension, it projected to a higher dimension, then it take it back to small dimension again, and we apply the scalar activation function. So that's what we do. So we know that even after here we're gonna get the same dimension. So then we have this window size, which is something that was hard for me to wrap my head around. But I think the purpose of this window function essentially, um, there's also unpartitioning, by the way. There's window partitioning, then there's unpartitioning. So I think this is to enable the attention mechanism to operate on a smaller windows of the input tensor, which can be more computationally efficient than operating on the entire input tensor. And I think that's what we break these input into smaller thing. I think that's what this is. I think. So I think we have this shortcut. I think that's all. The purpose of this is for residual connection. Then we apply these norm, and we check if window size. We have to apply the window size, which is greater than we have this x and paired higher than w. Then we apply this self attention that we did cover in more detail, which is this on the input. Then we know that we're gonna get the output. Then we unpartition this, um, uh, then we apply this multi-layer perceptron, including these, we apply these residual connection. I think that's what we're gonna do. But yeah, we're gonna return x, right? That's what we're gonna return. So I think we're still maintaining the same dimension even at this point. Nothing is, because of after this multi-layer, otherwise we wouldn't be able to do the residual connection anyway. So I think we're still maintaining the same dimension. Nothing has changed, right? So yeah. Now, I hope I'm not skipping most important things. Some of these functions here, like window partitioning, you can go through them, but I'm just telling you like the high level overview. So, like I said, I'll rather like tell you something what it means, because to some of the code, I think to get into it in much more detail is not as intuitive as I might want it to be. So yeah, so the things that I like to cover each line of code, to be honest, but it's not like I'm skipping each line of code or something like that. It's just that this window partition, I just didn't fully get it. Like by going through the code, I can see the purpose that it tried to break the dimensions, but the thing is, there was no enough comments. So just to kind of like explain something that I don't understand, I'll rather like tell you that I did not cover this, right? Sorry about that. I just hate to skip stuff, but in this case, this window partition, I don't get it that much. But honestly, I don't think it have like a huge impact into, in a way of like the main core. I don't think like it's the core or anything like that. I think it's just a technique to say that we want the efficiency of actually doing the attention, or then we want it to kind of like work on the smaller window. In this case, I don't think they use the flash attention. So we're gonna cover the flash attention, I think, in the future. So that, yeah, it's also quite interesting thing that they it's in the market. So anyway, we coming back. We're gonna backtrack, right? So we done with this block, and we know that it was getting used here. So we know what this block does. We're gonna create these 12 of these. Just imagine how like depth that is. Like, yo, that is so huge. So we're gonna create these 12 of these, and we're gonna put them inside this NN model list. And we have these NN.sequential, in which we are essentially going to take the embedding dimension, which is that 768. And now this is where the magic happens. We're gonna output it with we're gonna output it with this. We're gonna have the output channel, which is 256. This is the thing, 256, that I was always waiting for, because now we know that we're doing the right thing. That's what we're navigating the code the right thing, the right way, because that's like, wow, what we should be getting by the end of the day. Then we have this positive pointwise, yeah, pointwise kernel size equals to 1. Then we have this 3 by 3 kernel. The output here is going to be 256, and we're going to output 256 again. So that's fine. Just to kind of like walk you through the paper so that we can relate this. So I'm going to read this phrase here so that we can see that actually that's what it is. So they state that in general, the image encoder can be any network that output channel by height by width. So what does this mean? It means that at the final point, at the final of the image encoder, we should be having channel by height by width. In this case, I'm expecting that we should be having 256 by 64 by 64. So which is cool. Then they say that motivated by scalability and access to strong pre-training, we use the MAE pre-trained vision transformer with a minimal adaptation to process high resolution input, specifically the VIT16 with 4x4 windowed attention. Yeah, I think that's why now it makes sense. So this window attention, this is where I have to understand this. I personally don't. I never this. You see this window thing that I told you about. I think it's related to this VIT16. So I'll have to, but I think still think it's working on that. It's just like the same attention. It's just that maybe it's working on the 4x4 window. I don't know, guys. I don't know, but I think that's what it is, right? I'll check it out. But now that they're mentioning it here, it's quite interesting that I'll look into it in much detail. But I did go through the code. It's just that like maybe I was not. I just like understood it at the high level, not like at the detail level from the code. But anyway, that's okay. Then they state here the image encoder output is 16 add x downscaled embedding of the input image. Since our runtime goal is to process each prompt in real time, we can afford a high number of image encoder flops because they are computed only once, not per prompt. Which is, yeah, this is quite interesting. So essentially, you can think of like you're gonna output the image embedding, right? Then you can actually have as many prompts as you want after that, like because of you've computed this this image, which is taking time, but now that part is done and the prompt is very very fast. I think they say that it runs in like seconds or milliseconds, something like that, but it's way way too fast. It can actually run on the browser. Then they say the following standard practice we use an input resolution of 1024. We saw that, but scaling the image and padding the shorter side. The image embedding is therefore 64 by 64. To reduce the channel dimension flow, we use a one by one convolution, which we just covered now on the NN.sequential to get this 256 channel. So yes, they that's what we saw. They kind of like lowered the dimension from 768 to get this 256. And then we had this 3 by 3 convolution. Also, it's going to output a 256. So each convolution is followed by layer normalization. So yeah, that's pretty much what we're seeing here. So this paper definitely this layer normalization and all of the stuff. This is quite good. So what we do here is that we have this forward pass in which we're going to apply all of these things. I believe that here we're supposed to be getting um, wait, this is a neck, right? Yeah, it's a neck because you have this high dimension, right? You have this high dimension, then you have the output channel, then you're gonna have this output channel and output channel. So it's, yeah, that's fine. So I want to understand the dimension from this point here. So here, I believe that 0 is going to be the batch, right? Then I believe that this 3 here, because after the neck, we're going to be having 256, right? That's what we gonna be having. So I'm believing that this is gonna be 256. So it's gonna be 256, and this is going to be the first and the second one. So we knew, so this is going to be 64 by 64. Because of all this time, remember that all of this time we had a batch by 64 by 64 by C. All of this time. And we know that when we did C, we always called it 768, right? So now, because of this permute, we taking this obviously, when we process through the neck, we're gonna get 256. We're putting it here. Then these two, which is these two, one and two, they're gonna be on the last dimension. But anyway, we get this. So for each image, this is pretty much the dimensions, right? So that's pretty cool. So now we know what we do. This is like the VIT, and now we know what it does. But now let's go to the paper and see what's the next thing that we need to cover. What's going on? I feel like I don't know what's going on here. I can't scroll. Actually, let me do this. Can I do this? Okay, now I can. Okay, so it's gonna be the prompt encoder because that's what we need to do. So we need to understand how these tags, box, points, mask, they're getting encoded within these things. Then we're gonna break down into the mask decoder. Okay, so let's get into that, which is gonna be the prompt encoder. This is gonna be the code that we gonna have to go through, and yeah, we're gonna try by all means to understand. Some of the things that I don't understand, I doubt. Yeah, I think I understood everything. The thing is here, guys, this function, it bothers me because I didn't cover this, but you know what? I'll try to understand it then. Maybe I might come back after this, but I didn't understand this. But anyway, that's fine. We're gonna go now into the prompt encoder and we try to understand. So, getting into this prompt encoder, we can think of this as like the user is essentially going to prompt the model that this is the part that I want. This is the part that I want to segment within this image. That can happen in multiple ways. The user can have points, like you can like click on the image through points, or you can have a mask, or you can have a box, whether it's like through object detection. um, they also said that there's text, but I've never seen that in the source code. I think they omitted the clip part whereby they said that you can prompt it through text. So I don't think they included that in the source code. But anyway, this is what the prompt encoder is going to try to do. So it takes these image size and image dimensions, which we're going to see how they're getting used. And we have these activations function. In this case, it's scale. Then we have this first class here, which is positional embedding random. So you can think of this as like we want to embed all of these points, all of these prompts that we're getting, because we want to know where they lie within the image. So hence it's important for us to add some position to these points that you give to the prompt encoder. So how this works, uh, is that we have these number of features and we have a scale. So we're going to create a matrix here of 2 by number of position features, and we're going to scale that. And this is going to give us like a Gaussian matrix essentially, right? That's the first thing that we do. Now getting into like the meaty part of this is that we have this position encoding. So this position encoding essentially it takes a tensor coordinate, right, as input, which contains normalized point in a range of zero point 0.1. That's what the author said here. The first thing that we do essentially is that we're going to multiply this by 2 and minus 1. I think this is because we want to scale the coordinates to the range of -1 and 1, if I'm not mistaken. Then this chords is going to be a dot product between this Gaussian matrix, which we just spoke about right here. Then the resulting from this dot product essentially is going to get multiplied by 2 to the np pi to scale the values to the suitable range. Then we try to concatenate the coordinate. We take the sine and the cosine of this. Then we calculate. We have these essentially, right? So that's what we do, and we do that across the last dimension. That's why we have that -1 here. But essentially we're gonna get these coordinates, and we're gonna have what we call c, which is going to be the number of positional encoding features. That's what this function does. Try to calculate a positional encoding features. That's what it's going to do. And now we have this function here. So you can think of this as like we're gonna have an input, which is an image in this case because we can see it has a width and height. Then we're going to create a one. So we can think of we creating a grid of that image, but it's gonna be containing one. And from that, we essentially gonna create cum sum equals to 0 minus 1. So you can think of here, we're creating these across the rows, and we're creating like like for example, like say you have one, you kind of like continuing two, you kind of like three, but because of you have that -1, you have that minus 0.5. So this is going to be more like 0.5, 0.5. Then you kind of like accumulate that across the entire row. So that's what that does. Then you're going to do the same thing, but this time you do it across the column. Now you have these two matrices with the same shape as the image. Then you're gonna divide these to normalize them with the height and the width. Then now you stack these. We're using the stack, and you're gonna uh, have this dimension -1. So you can think of this as gonna produce a dimension of what it's going to be. It's going to be height, right? It's going to be width, and it's going to be 2, like this, I think. So that's what you are going to get in this case. And now we have these, we're going to permute this, right? To have the last dimension here and the height and width here. So that's what I think this is does. So the reason I'm saying the dimension is going to be height width by 2 is because of this dot product right here. So these two here, right? If we look at this dot product right here, so because of we have a 2 right here, so what is this? It's going to be torch dot matrix. So we have a 2, then we have number of pause. So it makes sense that the 2 from here has to be at the end because of we have want to apply the dot product on those 2's. That's why I'm saying it definitely makes sense. So that's why here the result is going to be more like height and width, and it's going to be uh, that 2 will be cancelled because of the matrix. Then we're going to have the c, which is going to be the positional features in this case. um, so what we do in this case is that we try to get the last this is no longer 2, but it's rather this positional features, and we get the height and the width, right? I hope this makes sense. All right, that's how I kind of like trying to make sense out of this, right? So now we going to look into this forward. I'm going to explain this. I know this might not be intuitive. Like you might be asking yourself, why are we applying cosine, sine? Why are we doing all of this? Where is this as getting used? I know that I'm gonna get into that. I just want you now to stay with me so that I give you like a high level of understanding. Then I'm gonna show you like a practical way and how it works in like the real scenario, so that you kind of like link that with. So I'm gonna show you. I'm gonna explain to you how these functions are getting called, where they're getting called. Just stick with me. in a second for now. So now we have these cards in this case. So these cards here, I'm going to assume that this is going to be, because of we have to apply the PE, so I'm going to predict that has to be badge, right, which is going to be a badge, then it's going to be, and so this is, we can think of this as a number of points. Then we're gonna have two, because we're gonna have to do that matrix multiplication there. So these two, you can think of them as like the x and y coordinates dimensions. Given a point, that's what the point will have. So that's why this two, it denotes essentially, as you're gonna see. So yeah, that's what we do. So essentially, we're gonna apply this, especially when we have the points, right? Uh, so for example, let's say you go to the model, you create your own point. We're gonna call this to encode those points. But sometimes, essentially, you don't need points, right? So now now I'm starting to explain the intuition behind this. So let me show you where this stuff are getting used. We're gonna explain all of this function. It's just that I want you to have the intuition first. So what we have, I said that we can have points, right? As you can see that we call in this. So when we have points, we're gonna call this one because we already have points. We don't have to use that like matrix, Gaussian matrix, pi, and all of that, cosine, and all of that. No. We don't have to. What I'm saying is that we don't have to use this one here. We don't have to create a grid. That's what I'm saying. We have to use this because you already have a point. So, right. I will explain that why we have to do that. Um, just so when you have a point, we use this one with chords. When you have a boxes, we use this one with chords. Then the mask, we don't have to because we're using convolution. We're gonna get into that also. But this is interesting. This is where we start to use it. We start to use that forward pass. And now, why do we use this one? Essentially, this is where we don't have points. We don't have anything that is given to the model. So now it's like the model is just going to create a grade and pass the points there based on the image. So let me show you an example. Let's go to meta segment anything. So I came here to meta and I'm going to go to demo. Yeah, this is the image, right? So if I go to uh, this is stuck. Let me see it. Can I refresh this? So I'm gonna say yes. So if I click on this dock here, essentially if I go to everything, you will see these points. Can you see those white things? Yeah, like it creates those white things. That's the grade that is the code is talking about. And I had to count them like manually. As you see here, I had to count them, and there's like 32 of these things here. So there's like 32 of these points, right? That's what these points do. So if I go now to the paper, uh, I don't know if I can find that bit, but there was a time where let me just go to that. You will see that they say that they're creating 32 to prompt the model. So it's like I think it's one of those zero shot scenarios, but I just want to show you in a second. Um, where is this? So this is not it. So don't confuse the dance prompt. So this is not the one. So this is just for the masking. So I think if I go to the zero shot, maybe I might see it 32, 32, 32, 32. I forgot where is it. Uh, yeah, I don't know why I didn't highlight it. Uh, but anyway, it's fine, guys. Yeah, but anyway, that's what they essentially did. Is that they had to create this. I'm just gonna ping this paper because here I can be able to search for it. Um, Anyway, yeah, you see, there is it here. They say specifically we prompt the model with 32 bit. Let me just zoom in here. So they say that specifically we prompt the model with 32 by 32 grid for each point created a set of masks that may correspond to valid objects. That's what they did right there. So that's what I meant. So the point anyway, what I'm trying to raise with the code was that this as much as it might look confusing, essentially we are creating this grid, which is essentially going to create those 32 points. That's what this code is going to do, I think, right? And now we're going to create those positions. But now, when you have your own points, you have your own points. We don't have to create that grid because you provided the points, so that's fine. So I hope this like positional thing how it works. They're using the techniques like cosine and cosine. These are like the techniques that we use to kind of like create positions. I think. On the transformer side of things, but I hope it kind of like gives you an idea of how it works. But anyway, so now we're continuing. Now that we have positional encoding layer, we are going to then create the embeddings. So essentially, you can think of each point will need to have the embedding dimension. And in this case, there is 4 points. And what happens is that we going to embed those points, right? And the reason I'm saying two here is because of two is going to be one is going to be positive and there's going to be two is going to be negative, three and four they are going to be for the boxes. Just to kind of like explain that more in a good way, I'm just gonna try to zoom in here so that we both understand this in a much more good way. So we have let me just make sure that I can actually highlight this. I'm just gonna insert my pen. So we have the positional encoding of its top left. So essentially, a box is represented by embedding layer, a position to the top left, right, with the land embedding representing the top left corner, and the same structure but using a land embedding structure to the bottom right corner, which is here. Then I think also the point, so there is it here. The point is represented as a sum of positional encoding of the point's location and one of the two land embedding that indicate if the point is either a foreground or a background. That's what it is going to be. So hence I'm saying four in this case because um, 3 and 4 will be for the boxes left and bottom. Then 1 and 2 will be for the points, which is going to be the foreground and background. So we then create embeddings dimension for these points. And so this is going to be a list of an embedding. So that's what we do. And then if sometimes it's possible that a point is not provided, so we need to create an embedding for that. So you're gonna see there's not a point, not a mask or something like that most of the time. So we then have this mask as shown in the image that essentially the mask will be projected through a convolutional layer. So as you can see that we create these conv and we have these layer norm and activations. Just to remind you also of this, I think this is the architecture right here. Um, so I think I just want to make sure that I link everything that most of the stuff that I say to the architecture here so that we can see. So the mask will go through this conv, and that's what this conv here starts with. Right? So we explained this. I hope I even showed you an example. I hope you still remember this just to get a dense encodings. Then we have these embed points. So this is where we get a prompt as points, right? So that's where then now we have to embed these and we have to embed these points. So, but here what we do is that we add 0 0.5. I think this is to shift to the center of the pixels. Then we have this pair, which is going to be a bool. If it's true, then we're just going to create these touch dot zeros and touch dot one with respect to the length of the points and the length. Then we concat these across the first dimension. Then we try to get the point embeddings that the user provided. So we provide the points here. Then we provide the image size. Then what we do is that we check the point if the labels is -1. If it is, then we set this to 0. Um, Actually, let me remind myself. I think -1 means I'm not sure. I can't remember, but I think 1 plus 1 was it referring to something does not exist. I think I'm not sure, but I think that's what it means. It's just that I'm not 100% sure. Let me check. Did I mention it in the paper? Minus one. I'm just maybe I missed that, but I think these labels essentially, by the way, they are represented by there's one, there's zero, there's minus one, and all of them like represent something. I think as you saw, like they could be a background, a foreground, or something like that. So no, they did not mention here. So that's fine. But yeah, essentially when we get minus one, we set these to zero. And what we're gonna say is that minus one, I think, is because of something does not exist. So we're gonna set it to not a point embed. So that's what this embedding is. We're gonna set it to this. So then we have yes, solve dot not embed. So it's wait. I think yeah, that's correct actually. Minus one. I think something does not exist. So we have this positional embedding, which is label is gonna be zero. Then we add this the first embedding here from the point embedding. So just to scroll you, just to kind of remind you, we added four things here, and I told you that the first one is going to be I think the foreground, then the second one is going to be the background, then the fourth is going to be the left, and the third is going to be the left, fifth is going to be the right, but the last two they are used on the box, then the first two they are used on the points. So that's why here you see zero and one because of these are the ones that represent the foreground and background, and the ones for three and four they're going to be used in their boxes because those ones are it's just that they're stored in one list, so to speak. So yeah, that's what is happening here. Then we return these point embeddings. Okay, but yeah, I think but at the high level you can think of here, we just say we take in the points that the user inserted, then we embed them, like we're creating some sort of like positions where they are in the image. And we do the same thing with the embed boxes. And by the way, I forgot to tell you all the dimensions. By the way, I think I should just make sure that I tell you all of these dimensions. Because there's way we get to understand in a much better way. So number of boxes, yeah, I think we're gonna get number of box 2 by 2, uh, because it's gonna be number of box, and we have 2 by 2, which is gonna represent the coordinates. Then what we're gonna do is that we're gonna pass this box towards this PE positional encoding layer, which is going to return us the batch by n by c. So B is going to be the batch, then n is going to be the number of points, then c is going to be the number of feature encodings. That's what we're going to get here. Then we apply these positional embeddings to these things here, the weights. We add them rather to these here. Okay, we return the corner embeddings, then we apply these embed mask. We can get a mask, and we if we get a mask, what we do is that we're gonna apply that self the convolutional layer. And I think here I'm not sure if they're gonna apply this. um, yeah, I think that we're gonna see this in the mask encoder. So they have to do an element wise with the image encoder. I'm not sure if it's done here, but we'll see. But I think yeah, they have to do that so that like they kind of like combine these two. But yeah, that's what they're gonna do. But anyway, yeah, I think we so far so good. So yeah, this is like the convolutional layer that I was telling you about. So we project these two embedding dimensions. Okay, that's fine. What's next here? We have the scared batch dimension. I think what we're gonna embed, we're gonna get the dimension of that. Otherwise, we're gonna set that to one. So that will be yes. Otherwise, we're gonna set that to one. But anyway, that is because if we don't embed something, if it's not a point or a mask, we wanna set that to sparsity. So we get the points, boxes, and mask. And what we do here is that if we have a point is not a none, that means the user provided the points as a prompt. So what we do that we're gonna embed that. Then the rest of other prompt mechanism, like boxes are gonna be set to sparse embeddings, and they're gonna be their thing is the thing called is not a mask will be initiated. For example, self dot not a mask will be applied, I think. um, then we have also the boxes going to be the same thing. Mask is going to be the same thing. Yep. So this is like self-explanatory, I think, guys, because like it's you can think of it as like if we're given a mask, then we're gonna apply a mask for that, right? So yeah, I think I explained everything this side of things. I think this was quite interesting, and it was quite easy to understand, and it's quite impressive because they say that this actually runs very quickly, meaning that it takes like milliseconds to run. So that's why we can actually be able to run this in the browser. The only thing that takes time is this image encoder. Sometimes if I pass an image, it can take yeah, quite a minute or so, or maybe a few seconds sometimes, depending on the number of people who are using it. But yeah, the VIT, they're quite very expensive to work with. So anyway, just to kind of like take you back to the paper so that we can recap, but we are close to kind of like closing this. I think there's still quite a few things that we need to cover, but I think we're making good progress so far. So we kind of like went through this image embedding, and we know that we were supposed to return this, and that was the image encoder. And we went through the prompt, right? So we went through the prompt, which is what we covered now. um, Actually, and I don't think I covered this, so I have to go back and cover this output token because and also prove it to you how we're getting the 256. I think I didn't show you that, so I have to also show you that the dimensions. But yeah, then what we're gonna do now is that we're gonna go inside the cross attention file. So the cross attention file is gonna apply these image to token attention, token to image attention, and we're gonna see all of this, right? And there's gonna be a self attention that we need to apply on this. Then yeah, this is gonna be quite interesting. So we're gonna cover the transformer file. It's not actually hard. uh, Cross attention, it's not that hard. I think if you understand the transform architecture, it's what we use on the decoder side, so it's definitely not hard. And it's a very easy file to understand, I think. So I'll try to make sure, if you don't understand, I'll make sure that you have an idea. So that's fine, let's get into it then. So now we're going to start with this two-way transformer. But before, I just want to say that we have this two-way attention block. So what we can do is that we can go to this and cover the attention first, then we can backtrack to these class. But before we do that, I just want to brief you on the input. So we have this depth in which is going to determine the number of blocks, right? Then we have the embedding dimension, which is going to be the channel dimension for the embeddings. Then they have the number of heads. So I think in this case, actually, they're gonna use a small number of head. I think in the paper they mentioned because of the computational cost. Then we're using ReLU this time instead of GALU. Then there's a tension sample rate, which is going to be 2. So what I want to do is that I want to scroll down to kind of like start with all the dependencies of these functions first. For example, the attention block depend on this attention. So it's better if we start with the attention. So I know that this might sound like repetitive because the attention is, we covered this in the VAT, but I'm just gonna walk through it so that you kind of like have an idea of anyway. So we have the embedding dimensions. In this case, I'm assuming this is gonna be 256, right? Let me just verify from the paper. So I'm just gonna scroll down. Just gonna make sure that we are on the. I'm assuming that this should be 256. The cross dimension, the image embedding is stated as a 256 dimensional vector. So I'm just gonna scroll down because of that's what the image input is gonna be. So I think, yeah, I think this might be the one, right? So it's this one here. So it's gonna be the transformer uses an embedding dimensions of 256. Then the transformer MLP block is going to have a large internal dimension of 2048. So yeah, we're gonna get there. But I just needed to verify that so that when we start doing the dimensions on this code, we know what we're talking about. So anyway, we have these number of heads. I think they're gonna be passed through also. Then the embedding dimensions, then this is going to be the down sample rate on this. Then we create these query key and value in which we're going to pass in the embedding dimensions alongside the internal dimension, which is going to be um, this. I believe that this will be similar thing to number of heads. Looks like it, yes. um yeah, so there's no remainder here anyway. Yeah. Then we have these output projections, which is going to be self-taught internal dimension. Then we're going to project these to the embedding dimension, so the same dimension that we inputted. So that's fine. Then we're going to have the separate heads in which we're going to take the input, and the goal here I believe is to create heads, right? So we have this batch and channel, and then we're going to divide the channel by the number of heads, and we're going to create this extra dimension here called num heads. Okay, so you can think of this. This is like a similar attention operation that we always do. You can think of this as like we're projecting these into number of phase. That's why you see here C is getting divided into the number of phase. So this dimension here is going to be projected into these number of phase. Okay, so the number of heads in the paper is just to kind of like link everything here. I know that they said that they're using a small number of head mainly because of but I'm not sure where is that. But anyway, I don't want to come and back and forth. I think that might be confusing for you guys to understand. But yeah, let's just assume that I don't think they. Okay, they say all attention uses 8 heads in this case. So yeah, it's not 12 compared to the VIT. So that's what they're using here. So that's what we have here in this case. So that's what we're going to be. Then we have this recombine heads. So this is going to be the last component, because now we, after we apply the attention, attention dot product value, then we're going to need to recombine all of these heads. So that's what this function we're going to do. So it's like we kind of like going back from after applying this. So that's fine. Then we have these, we're gonna get query key and value, and we're gonna project them like so, right? Then we separate these into these self number fields. So we project these query and head these key and values to these number of heads, right, using this function. So that's what we're gonna do. So you can think of like this, what is it, where is it, yes, the dimensions of x is gonna be projected into number of heads, I think. Yeah. Then we have this attention here, which we're gonna say q dot shape, which is query dot shape. Then we're gonna take this q and we're gonna have a dot product with k, and we're gonna make sure that this is gonna give us this dimension, which is gonna be the batch by number of heads by n token by n token. So that's fine. So here you can think of this as like we have each token, we understand the like for all the tokens, we kind of like have, they have their own importances. Like token has like importance across all the other tokens in the input sequence. So this way, we get to have we get to understand like which tokens are related, or they depend on one another because of that importance. That's what I think this means. So we kind of like went through this, I think, in the VAT, but that's why we're returning. So you can think of this as like number of patches, but that's what I said in the VAT. So that's why it's n tokens. But anyway, we scale this. That's what we do. We're gonna apply the square root. We're gonna divide by the square root. Then we apply the softmax of these attention across the last dimension. Then we apply a dot product on the value. So you can think of this as like the query, like I said, is what I'm looking for. Then the K is what I can offer, V is what I offer. Then we apply this recombine heads. Because of this transformation is happening on all of these heads here, right? So now we need to combine these heads, and now this is what it's going to do. So what this function does is that it's going to take X, which has this batch number of heads token by and C pet head. Then we transpose this these two columns, right? So we transpose these columns, then we're gonna multiply the n heads by the C. So this is gonna give us B by n token by C, right? This is batch number of token and dimension. So yeah, okay. So you can think of like each token here has a dimension. That's what this is means here. So we have the output channel, so which has to take our dimensions, which is going to be the internal dimension is going to project it to this dimension. So this C, it's this internal dimension because of it makes sense because of um, that's what these V and queries where they is it here, these V queries, and they were operating on this internal dimension when we were working with heads. So I needed to emphasize that because I think that might be confusing. And so that's what we get. And here, essentially, after we apply this, our dimension is going to become where is this? I'm just gonna scroll down. Yeah, so our dimension here is gonna become batch by n token by embedding size. So it's gonna be um, B by n token by token by what's this? It's gonna be the C, but I don't want to write C because it might be confusing. I want to write this is the embedding dimension here. This is the one. I think it's 256. If I'm not mistaken here, so 256. That's what I think we going to return. So this is the attention. Pretty much we are used to this now. So that's how it works. So we're gonna backtrack and we can see that actually it's being used here. So now the question is, what is this two-way attention block, right? So that's what we're gonna get into. So just to give you like, just to read the paper for you so that you understand. So how it works, so why is it it's here? So you can think of you see here they say that each decoder layer performs four steps. So this is the self attention on the token. So this is the first thing. Then we have the cross attention from token as queries to the image embedding, and the point was multi-layer perceptron to update the token. Then they say that we have a cross attention from the image embedding to the token. So now the image embeddings are the queries, right, to the token. But also the first cross attention, it's whereby the tokens now are the queries. So we kind of like go this in an opposite direction, right? So that's what that does, that essentially the cross attention. So now let's look at it from the code and how this is done. So the first thing that we do is this attention here. So we take the embedding dimension and we take the number of hits. In this case, this is the number of hits in the attention layer. Then the embedding is like the tunnel dimension of the embedding. That's what we do. So here, like we spoke about it now, we know that we're gonna get, just gonna copy it so that we don't forget. We have to get this B by n token by C. Yeah, when this is going to be applied, no, it's not being initialized, but when it's going to be applied in the forward parser, we're expecting that. So then what we do is that we're going to pass this in this we initialize this norm with this embedding dimension. So I believe that this embedding dimension is this 256 in this case because of it has to be consistent. That's why it has to be applying across this. So that's what it's gonna be. So we have this embedding dimensions, and the attention is gonna take this embedding dimension, number of hits, that sample, and we have this self attention to self attention token to image. So yeah, that is like the tokens are the queries, and we're gonna have this part whereby the image are the queries. So that's the key difference essentially between these two. And we have this layer norm 2. So this is layer norm 1, and it's going to have the embedding dimension, which makes sense. We just need to maintain this 256 across these platforms here. So we have this multi-layer block in which we're going to pass the embedding dimension, and we have this multi-layer perceptron dimension. What's the size of this? Oh yes, they said it in the paper. It's going to be 2048, right? So yeah, they did mention that. So we kind of like going from a small, we're going all the way up, but I'm not sure what this will return. Let me just, I know that we went through this, but I just want to it's gonna take okay, yeah, it's like a yeah, I remember this. I said it is more like a bottleneck. So we go from small, we go up, then we kind of like project back to small. Okay, yeah, yeah, this is makes sense. Then we apply the activation function. So yeah, we still maintaining the same 256, just that this we go up and we come back to the small dimension. Then we have this layer norm that is going to be applied, and we have this layer norm 4. Then this is whereby the image are the queries, like I said, to the tokens, and we pass these inputs right here. So yeah, we can see that we're reusing the same attention. So this is that's why I said this is not actually hard, because it's just like we kind of like different objective, but the same code still works fine. Yeah, that's that. So what we do now is that the first thing that we're gonna do, I just want to make sure that, okay, before I go there, I just want to show you this image. So so what's going on here is that this is like the cross attention in the antenna. So I had to show you this because I feel like though, just to make sure that for those who don't understand this, but essentially you can think of like we can have the key and the values coming from a separate attention, like or an encoder or something like that. Then we can have the query coming from a separate also attention. Then we just need to have an attention mechanism that is going to apply these two. So that's what we're gonna do, and it's important for me to emphasize this because you will see that after we apply an attention mechanism, we keep the query of that. We keep the query, and we're gonna actually apply that against the keys that are coming from an image or something, or token, something like that. So I needed to show you this so that you get to understand it from a visual perspective. But anyway, that's that. Now, we have this thing called skip first layer block, in which we're gonna have this self attention with the queries and keys and queries and keys and keys and values. Yeah, so that's what we're gonna get from here, right? And else we just gonna add the queries, and we're gonna get the positional encodings, and we going to apply the self attention on these. Then we get these attention output, then we add the attention output here with the queries. This is quite important, and we still maintaining the queries here. So otherwise, what we do is that we just apply the self attention, right? And we get this queries. So this is going to be our queries. So we don't necessarily add it to the attention. So self dot skip first layer positional encoding. So I just want to understand this intuitively because I want to make sure that it makes sense. So I'm gonna scroll up. So I'm gonna believe that essentially when we loop through, so I equals to 0, So this is going to be true. So it makes sense. So that means that you see this is a loop. So because of now we're looping through all the blocks. So the first one is going to be zero. So it's going to be true. Then the other ones are going to be false. So because it's going to be one, two, three, just like that. So which means that we don't want to add positions, uh, query position encodings on the first layer. That's what this does essentially. Then we have this, we normalize these queries. This is, we apply this norm1, and we're gonna get these queries. So you still remember the image that I showed you, which is that now we have these keys and we have this soft attention. We pass these queries, and we get these keys from a different, these keys are coming from, it could be an image, right, or something like that. But the point here is that that's why I showed you this image. It's like these queries might be, these keys might are coming from an image, and this query is coming from the tokens, and now you have to add them inside this attention. That's what cross attention is all about. So that's why I needed you to understand that. So now these queries here, we add the positional encodings, and we can see that they're gonna add this positional encoding every time. So this is just to enforce positions within attention, and these keys are also added. So these keys are coming from, I think, image, because here we try to cross attention token to image. Yes, so the query here are the tokens, meaning then the key here is going to be the image. Then this is the value which is going to be the key. So just to explain this intuitively, so you can think of this as like we're asking ourselves, because of queries, what I'm looking for. So it's more like the token is asking the image that what am I looking for. So it's like from a simple English, we can say that given a prompt, we want to understand, right? Or given a prompt, we want to understand from an image, like, what is that segment that I want, right? So from that image. So that's what I think it is. Then the keys is what I can offer. That's why here we're using the keys from the image, because of we want those important things from that image. Yeah, maybe my explanation is horrible, but I'm just trying to make sure that I explain in a much more intuitive way. I feel like this way maybe it might help to understand for a long term. So then we apply these, as always, we add these attentions to the queries. Now the queries updated with this attention output. So we're gonna normalize them. As they said that we need to update our tokens. So what we do is that we apply this multi-layer perceptron on the queries, then we're gonna add them, and we apply the norm. So yeah, normalization is quite important, and adding these up the output is quite important. So this is like a repetitive thing now. Now this is quite interesting. This is why they call it a two-way, because now you see what's going to happen is that we have these queries, but now these queries are passed as keys. You see here, not necessarily as queries. Then the keys are passed as queries. So it's like now we're turning the table around. It's like now the image is gonna be the one that is the query is gonna ask, what is the things that I want from these tokens. That's the image now is asking. So the token is like, these are the things that I'm gonna give it to you. So it's like that, right? That's how I understand it. So we have these keys and we have this attention output. We, as always, we add them up, and we have depth norm. We normalize these, we return the queries and the keys. So that's all it is to this. And yeah, so applying these multiple transformation across, right? So just want to scroll up. So we're gonna go to, what is this? So this is the two-way, right? We kind of like have an idea of this. Let me see, was it taking, yes. So yeah, I still think we're still maintaining the same. Yeah, because of these are the same attention function. We're still maintaining the same dimensions. So there's nothing has changed so far. So I think we're still maintaining the same dimensions because we're reusing these components. We know that because of like putting same dimension, and if like this is the expected one and we reuse that, then we're gonna get the same thing. Anyway, as you can see that it was fast actually going this code because some of these stuff are easy to understand. Yeah, sometimes these stuff can be quite hard, but I feel like also, guys, I want to take a pause and say thanks to Meta. These guys always write a very nice code. So if you want to follow along, their code is quite clean, and they write a very nice code because it just easy to follow along sometimes, and it makes it easy to understand. And they always been consistent writing code like this, and which is I pretty like it. So yeah, it's nice actually. I'm learning also the best practices when I go through the source code. So anyway, we know that we're going to apply this for the number of these blocks. Then we are appending this into self.layers. So this is the module list. I see this is fine. Then we apply the final attention token to image. Yes, so we still want the token to attend to the image. I'm just going to show you that. I mean, that might come as a surprise to you, but actually we do, as you can see from this image here, just to zoom in. So we have this block here that I didn't show you. So it's just, I didn't cover this. So this is the token to image. So we still have this. Some of the stuff, I won't lie to you, I don't understand like they are intuitive, like, or they are reasoning. I think maybe they did mention, but sometimes like they don't say why we, like some sort of like a reason. It's like we adding stuff, but sometimes we don't say why we do them. So I like the intuition behind certain things. This way at least we get to understand, but I assume there's like this is like to get the final token to attend to the image, and kind of like a more robust thing to do maybe. Then we apply this layer norm to these embeddings. So this layer norm is gonna because of now we know that this is retaining their embedding dimension, so this has been consistent, so we're gonna get the same dimensions. So that's that. But this is where actually we're applying everything in this case. We have these image embeddings here. Then essentially we're going to flatten them, and we're going to have this image positional embedding. So this is just coming from, let me see, I just want to make sure, yes, it's coming from here. It's a tensor here. Yeah, so the positional encoding to add to the image must have the same shape as the image embedding. Yes. So we're gonna pass that inside them. Um, then we have the queries and we have the keys. So this is the point embeddings. So these are the things that we covered, just to kind of like link what I'm saying with the things that we already covered. We spoke about position, what is it, point embeddings. So this is like the point embeddings. Then this is the image embeddings, also from the VIT. So yeah, that's where, because of we have to like kind of like have these two things to communicate, because the point is like this is what I want, the image is like what I can I offer, something like that. So that's what this is all about. Then we kind of like go through these layers. They call them layers, but they should be yeah, these are like blocks. So yeah, these are like but yeah, then we have these, then we get these queries and keys, right? That's what we get. Then we going to have apply the final attention there from the points to the image. So we have these queries and we add the point embeddings. Similarly, we have these keys and we're gonna add their point their positional embedding. So one thing that you can realize here is that you can see that every time we apply these positional embeddings, especially before we apply the attention. This is to make sure that like the attention knows where each patch lies and the position of each patch. So we kind of like enforcing this. So I think this is one thing that I am learning from this. Is if I think it's kind of like making more robust attention mechanism, so to speak. So that's what they do in this case. So yeah, the tokens in this case are the ones that are the query. So this is the same thing that I spoke about, which is that this was the final component that they do. um, then we have this self dot normal final attention, which we have, which is the normalization. Then we return the queries and the key. So just to go back to the paper, kind of like look into this, we have, yeah, this is the final part. So yeah, we're gonna have to go into another component to see what's going on. But yeah, we went through this file very fast. I feel like it wasn't that bad, to be honest. Like, I feel like that is because of like we're starting to understand like attention, we're starting to see patterns, and now like when we start to kind of like go through some of these files, things are starting to make sense. Most importantly, we have an idea of the paper, and we can actually be able to understand which part relates to what. So that's why now it becomes easier as we go deep into the paper, because we things are starting to seem like they coming together. So now, which is the next file, which is this, which is going to be the mask decoder. So it's not that lot. Oh, it's a lot. It's 176. So yeah, this is the file that we have to understand now. So now this mask decoder takes the transformer dimension and including the transform module. Then we have the number of multi-mask output. So in case you're wondering why we have multiple mask output, if we go back to the paper, actually I forgot to cover this also. I think it's one of the critical things that they mentioned in the paper was to resolve the ambiguity. So by ambiguity, I mean, for example, a prompt. For example, let's say you have an image like this, and you just select a point. For example, you just select a point like so. We don't know if you want like the leg, or you want the full body, you just want the eyes or something like that. It's a very ambiguous or something like that, right? So now what they say is that if we output multiple mask in this case, like we select probably like top three based on their observation, they saw that actually top three are always on the correct side. So so that's what they observed. But anyway, I just want to show you that part, that passage. So there is it here. So they state that resolving ambiguity with one output, the model will average multiple valid masks if given any ambiguous prompt. To address this, we modified the model to predict multiple output masks for a single prompt. So this is what this was my point here. So we have like multiple masks for a single prompt, and we find that three masks is sufficient to address most common cases here. That's why you see in this case they have this three right here. So I hope like the intuition behind this makes sense. So we have the IU here hidden dimensions. Then we're gonna get into those now. Anyway, these are just definition. But anyway, we have this IOU token. So this IOU token is gonna be an embedding, which is gonna be one, and we're gonna have which is gonna have the dimension of one by transformer dimension. So you can think of IOU, which is, I think this is actually one of the widely used metric, especially in computer vision. So it kind of like measure the similarity between two set of bounding boxes or masks, right? So it help us to access the accuracy of an object detection or a segmentation algorithm. So it's calculated as like the ratio of the area of the intersection between the predicted bounding box and the ground truth bounding box to the area of their union. So that's how it works. So let me just see if I can probably find an image on the internet. I'm just gonna. So I don't know if you guys know this. I just wanna just to be on the safe side, and uh, but I'm sure most of the people have an idea. But I just, just to make sure that you have an idea, so I'm just gonna pull an image here. I know this might sound, maybe it might be redeemed as unnecessary, but anyway, that's what I was talking about here, right? It's like this area of overlap and area of union. So we try to see the overlap of the predicted and the predicted bounding box and the ground truth. So that's what I was referring to. But it's more like we're trying to assess our model, so to speak. I hope it kind of like give you a better understanding if you didn't know it, which is, yeah, that's okay. So that's fine. We have this. So this is going to be the mask tokens. So as stated here by the author, they say that obviously this mask decoder, the goal here is to predict the mask given the image, uh, given an image and prompt embedding. So that's what we're going to do. So all these things that we covered here, given these two things, we want to predict the mask. So clearly, if you have watched the video up to this point, you have an idea of like what this is. What we do now, we have this output sampling, which is going to be consisting of convolutional layers here. So we can see that actually they're using this transpose 2D convolution. So this is actually good, especially if you want to upscale or something like that. So I know that just to kind of like explain it in a more intuitive way, because I feel like um, I just need to give you a better perspective of how it works. So, how it works, let's assume that we have like some sort of like stride, which is equals to 1, and we have padding, which is equals to 0. And let's assume that we also have an input, which is gonna be, I'm just gonna be, it's gonna be a 2 by 2. It's fine, 2 by 2. Then we can have a kernel which is also going to be a 2 by 2, so that's fine. Then we can have a stride of 1, that's okay. Then the padding is going to be 0. So what will happen then is that we're gonna be having because we're gonna be what we're gonna do is that we need to now convolve, in which this value here has to be multiplied by these other values here. So the first part is that this is number one for this part. I'm writing it with red. We're gonna generate the numbers here. Like we're gonna multiply it by this, we get a number. We multiply it by this, we get a number. We multiply it by this, we get a number. We multiply it by this, we get a number. You can see that I have created a 3 by 3. That is because of this stride. You'll see my intuition now. Because of that stride, I have to add another one here because the stride says 1. So we need to move another one more. So now we are here. We are on this block. And its stride is 1. So which means that now I have to multiply this. We're going to put it here, 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 like so. And you continue doing this. Now you can like see the pattern. You continue to do this for all of the values in the input. So now you're gonna come to this value. So you do the same thing. So you're gonna be same thing that we spoke about, right? So you're gonna do it. Then when you are done, you can assume that we have these four boxes because we have four inputs. You can assume that we have four boxes like so. After we done our transformations, then we're gonna add all of these things up, right? We're gonna like try to add them, like all of these values that are inside these block. But by the end of the day, we're gonna be having a 3 by 3 matrix. So just to kind of like explain it in a more good way so that you can have a robust understanding. So it's still the same concept, even if like I feel like the stride is the one that kind of like help us to expand. So if the stride this time was 2 and the input is still the same, we have that 4 by 4. um, two by two, sorry, and we had this kernel which was also two by two. So it's still gonna be the same thing because we need a block to move twice because of that stride there. So what we're gonna happen is that we're gonna create this. What is it? A four by four, right? It's gonna be four by four, if I'm not mistaken, like so. Then the first value multiplies with all of these values within the kernel, and it's gonna accumulate all of this block here, right? And we do the same thing just like that, and we add. But we can see that now this output is much bigger than the input. So that's how why they saying in the paper. If we go back to the paper, um, we try to scroll down. I hope me going back to the paper is not annoying because some people might feel like I keep on going back and forth. The thing is, I'm going back because I want to show you where I'm getting stuff. If you're going to go through the paper, you just know where to get it. Um, anyway, where is it? It has to be here. Yeah, I think it's here. So they say that the transposed convolution used to upscale the output image embeddings are 2 by 2 stride 2 with output channel dimensions of 64 and 32, and they have a GALU activation. So that's why they're doing that, right? So, and if we go to the diagram, in case you're wondering where in the diagram or the architecture that is getting used, just to remind you, it's getting used. Where is that architecture? Did I? Oh no, I missed that. Um, um, okay. I think maybe. Oh wow. I apologize, guys, for this. I know that it might be not nice for me to scroll. I'm just looking for that because I want you to understand it so that you can always picture it in your mind so that when I explain, I can't find it. Surprisingly, I don't know why. And it's quite important because it's like you're gonna see that we apply this after that image. What is it? Yeah, this is it here. So you're gonna see that this is like the convolution that I'm talking about. So this is this part right here, and we can see that we're gonna have a dot product uh, with the output. So we covered this part within that code of the prompt. What is it? Yeah, it was the transformer. Then the output token per mask will have this multi-layer perceptron. We're gonna have a dot product with these two to get the mask, and the IOU scores we're gonna get them. So if now I scroll down, where's the code? There is a code here. If I scroll down, I'm supposed to get the mask, yes, and the IOU, which is true. So that's why I'm seeing here. Um, so we have these multi-layer perceptron. Yeah, these are all the all these multi-layer perceptron, I think, that we saw now. So yeah, we're just generating all of these. Then we have this IOU prediction head. Um, that's that. So this is going to be the forward pass, which is essentially gonna take the prompt. It's gonna take the prompt. It's gonna take the image embeddings. Uh, this include the sparse prompt embedding and the dense prompt embeddings. So as you can see that this is actually correlated with what we covered. I think retaining these right from here. So this is what we retaining from the prompt embedding. So we know that the sparse means that um, these are all the stuff that were not there because of we just set these. For example, if points is not none, that's what we're gonna prioritize. Then these bars, I think they replicating something that does not exist. Like maybe the mask is not there, the boxes is not there, something like so. Um, yeah, I think so. Anyway, we we pretty much gonna predict the mask, then the IOU predictions, and this is the function that does that magic. Um, but yeah, I think that's that. I think this is just a multi-level subtron, which pretty much going to have these linear layers and activation functions. Yeah, I think that's that. I think the reason here we have a sigmoid is because of we want the confidence score. So that's what we have there. But yeah, I think guys, I'm just gonna call it off. This video is like already 2 hour long. I just didn't. I think it's gonna be 2 hour long if I continue. But anyway, I feel like the core of this code we have went through it. So this is was the modeling part, and we went all of these files, and these are just utilities like to convert the model to ONX. I think I'm just gonna walk you through these folders in case, just to show you that the things that I didn't cover, but they had to do with like converting the models to ONX for efficiency. Then these are like demo notebooks. I think for predictor examples, you can go through these just to see all of these how these stuff work in action. So, but the point that I'm trying to make is that the core of this, I think we did actually go through it. Then we have predictors. I didn't cover this because also it's I believe that it's also just like integrating all of the things that we covered. Um, but yeah, if you're interested, I think you can look into those. But I feel like I just focused on these modeling because I was fascinated by following this architecture that you're seeing on the screen right now. But yeah, anyway, um, if I didn't cover things impressive way, I apologize for that. I'll try by all means to improve, and hopefully I get good with time. But yeah, I think that's what I can do for now. I'll probably write more a blog to explain things that I didn't cover, and I think maybe they are important. But for now, I think all the core have been covered. So yeah. But anyway, thank you very much. I'll see you in the next one. Bye.